So in this video, we will analyze a sample of nickel with a fairly thick amount of gold deposited on top. Find the data here in number one in the list here. We have survey spectrum. We also have a reference of gold, which we'll return to after we've done the analysis without the use of a reference. So we have the survey spectrum of the unknown sample with some gold deposited. We have the gold 4D, we have gold 4F here, and we have some nickel peaks here, the nickel 3S and 3P. So they are mixed in with this. So this is a fairly complex analysis. It's much simpler with the gold 4D. Here we have the O's here from the nickel, and here's the nickel 2P. So we will analyze the gold 40 and the nickel 2P because they are free from interfering peaks. And to do that, we first hit correct here. This allows us to read in the spectrum and make a correction for the transmission function. That's the first step. So the analyzer transmission depends on the energy, the kinetic energy. And for hemispherical analyzers, it's a good approximation to assume it's the energy to the minus 0.7. You can change this if you want to, but it's not so critical what you use. So we do that here. Now we have a new spectrum which is corrected. Now we start to isolate the two peaks. The gold 4D first, isolate peaks. We zoom in here to do that. We zoom in here like that with the mouse. Use your way. Put in the background line here, and now we have to fit that out here in this region here. So I fit it here, put in the slope. Now just look at this range here when I fit the slope. Don't look at this. Just look at what we have here. Defines the slope. It's not very critical how you define the slope. A little bit up or down will not change your result much. You can make the test for yourself and make analysis with slightly different slopes. But you fit the slope out here and moving it out. We have a good slope here, and then you move it in here. Because you sort of have to imagine what would happen if this peak was not there. The background would follow this line, right? Therefore, we subtract that now. And when I hit subtract here, it will subtract this line from the spectrum, and will do that in the energy range determined by this dot here, and whichever is furthest to the left, either the end of this line or the spectrum. In this case, it will cut it here. Right? So we subtract the line, and we have it here. This is the default file name. We change that to gold 4D and save the spectrum. When I hit save here, it will turn up here like that. Set the next peak, and that's the nickel peak here. So I first zoom in here. I fit a line to this region. Background line. And here we have some oceans coming down here. So I fit it in sort of this region here. Maybe slightly less here, corresponding to what we have here. And then like that. Subtract it, and we have now the nickel 2P. And let's save that. We have the nickel and the gold peaks here. We can hit cancel here and cancel to get back to the main menu. Now we hit analyze and we click gold first. So we analyze gold. We expect it to be a thin layer of gold on top, or maybe a thick layer, we don't know, on top of the nickel. So we need to input an IMFP. So we use the Quarsys IMFP calculator, which is based on the Tanuma Powell and Penn algorithm. To do that, we first find gold here in the list. So we find material, we find gold, and that's here. We have an energy here of about 11 something. You can see the energy up here as you move the mouse. So when I put that here at the centroid, we have 1140. So I put 1140 here, and we have 13.5. I put that in here, 13.5, and we're ready to do the analysis because we have angle of emission, it's normal emission. In this case, we use the universal cross section because we have transition metal. We don't have a polymer, silicon, or aluminum, germanium. So this is a good approximation. And the gold, as we expected, it's on top of the nickel. As we increase the thickness here, we see we can meet the line here, but not on here. We don't fit the background out here. To do that, I need a larger overlay, but then it doesn't fit here. So it doesn't really fit. If I try to fit it here, it doesn't fit here, and the other way around. But we can say roughly from this analysis that we have about 45 angstroms of gold on top of the nickel. But the fit is not so good, so let's try to make this better. We can put in two thicknesses by using the island model here. Let's start with 2 islands. And now if I put in one island here of maybe 100 and something, and put in a coverage maybe of 20, and another island here of 10 or 15 maybe, 20, 15. It's fairly good now. It's clearly a lot better than what we had here. So the conclusion is we have formed islands on the surface with about 150 angstroms height for the tall islands and about 15 angstroms height for the small islands. We cannot determine the absolute coverage of the surface here without calibrating the spectrometer. But we have determined the height and we have determined the ratio of the 2 islands, the relative coverage. I'll illustrate that by changing this, dividing these by 2 instead of having 20, 60% coverage. I'll change this to 10, 30. Simply divide this by 2. Do that here and do that here. And you see we get exactly the same quality of the fit here. What has changed is these numbers here. So we need to compare this to a reference spectrum to calibrate the spectrometer. So we can turn now to analysis of the nickel peak. I hit nickel here and buried layer. We expect nickel to be thick. We have a thick nickel, we have something on top, and sure enough this is roughly what we get. As you can see here, we need to change the IMFP. We use the calculator, find nickel. Now if I click find material and put in nickel, it will find nickel oxide because that's what is the first nickel in the list here. So it always searches downwards. So to find nickel, I can start here and then I can find nickel by searching again. We have nickel. We need it at the energy. We see the energy up here, and the energy at the centroid of the nickel 2p is 620. So we put in 620. Oops, 620 for nickel, and we have 11 angstroms. So I put in 11 here. And what do we find? We find we have about 15 with 5, 10. Starts to fit better in this region with 10. With 15, it fits reasonably well everywhere here, a little bit above here, but overall it's a fairly good comparison of the background. Very good fit, not a very good, but a comparatively good fit compared to the noise level. So when we compare to what we had with the gold 4D analysis, where we had 2 islands, we had the tall islands of 150 and the small islands of 15 angstroms height. Here we only find 15 angstroms. Let's try to model the other possibility where we had like 150 something and 15 angstroms and different coverages. I can change the scale here so we can see what's going on. So we have here, this part is now the gold from the thick islands, and this is the small islands of 15 angstroms height. So fit is quite good. When I change the coverage, you remember we had maybe something like this uh, distribution of the islands, the tall and the thin islands. The fit is reasonably good here, the same, more or less the same as we had with the buried layer here. What happens here is that you can see that if we change the coverage here, larger and larger, uh, it doesn't change, the fit doesn't change, but the intensity here changes quite a lot. Follow the intensities here and you see that changes as I move down here. The reason is that the electrons, the nickel 2p electrons excited here, go through the tall gold islands here, and we see practically nothing up here. So these don't really contribute to the spectrum in this energy range. They have lost a lot more energy on the way out, and they're further down in the spectrum, outside of the region that we're analyzing. So we only see those electrons that are excited here and go through the thin overlay. And therefore we cannot determine the coverage unless we calibrate the spectrometer. We could calibrate the spectrometer by using cross-section photonization cross-sections, or we could use the reference spectrum from a pure nickel sample. Fortunately, we don't have a nickel reference sample in this case, but we'll illustrate in the next video how you use the reference of a gold sample to analyze the gold 4D. But the conclusion is that we have these two islands and we have a consistent analysis from the nickel and from the gold 4D analysis, even without the